All right, all right. So we learned about points, lines, and planes, a little bit about angles and parallel lines. So now we're going to jump into the next step up and we're going to start making two-dimensional figures. So we're going to start talking about triangles. And triangles is pretty important to us. It's kind of like in algebra when you learned all about lines to begin with. Triangles are like the lines of algebra. We're gonna talk about everything we know about triangles. I mean, and it's just a brief overview. We're not going to go too far in depth and things like that. And again, there are no proofs. Okay. But we're going to talk about everything we know about triangles, from the basics to some of their properties that I feel you should know, which will help you get through the homework and things like that. So that's what section 10.2 is all about. It's all about triangles. So let's go ahead and get started. So that's the symbol for triangles. Instead of writing the words, I will use that symbol right there because I'm lazy. So down below, here's what we know about triangles. Okay, and in class, I would generally have you tell me all this information, but you already know this. You know that it has three vertices, so like 1, 2, 3. It's got three sides. 1, 2, 3. It has to be closed. Okay, because if I had something that's drawn like this is not a triangle, even though it's got three sides. Okay, so the fact that it's being closed is what really makes it a triangle, meaning that that's really what creates those three vertices. Because if you see this, I only have two. I've got vertice 1, vertice 2, there's no third one. So closing it up helps create that third vertice, and there are no curves. So all the sides are straight. Okay. What's cool about the triangle is that it is the smallest polygon and our strongest shape. Generally, when construction happens, and you can see this on bridges, bridges form what we call trusses, and trusses are triangles because triangles are our strongest shape. Okay, every other shape is extremely weak except for the triangle. Okay, it's kind of cool, and it is our smallest polygon. We can't be any smaller than that because how do you make a polygon with two sides? That's weird. Polygons have to be closed, okay? Meaning no gaps inside it. So the smallest shape that we can make that is closed is a triangle. All right. So let's talk a little bit more about triangle. You know that there are different types of triangles, and we name triangles according to their sides and their angles. Okay. Now, the sides, you guys are pretty good at naming because, again, in class, I would have you all name the different sides and the angles that we know about. So, like, for instance, sides, we know that there are things called scalene and obtuse. Okay. Scalene means none of the sides are congruent. Isosceles means at least two sides are congruent. And again, that's that symbol for congruent we talked about. Okay, so scalene, none of the sides are congruent. Isosceles, two sides are congruent. And you all are pretty good about remembering that there is what we call an equilateral triangle, which means all sides are congruent. All sides are the same length. Okay, remember, congruent just means same length. So for sides, it either has no sides congruent, at least two sides congruent, or all sides congruent. Okay? Now, the angles, let's talk about those. Again, like I said, you guys are pretty good about knowing the angles. For instance, the first one you generally tell me is the acute, which means that all the angles are acute angles, okay? Less than 90 degrees. All right, so you got acute triangles. Then you have what we call right triangles, where one angle, only one, is a right angle. Okay? Can't have more than that because if I had two right angles, that would be 180 degrees. And you all know that inside a triangle, all the angles add up to 180 degrees. Okay? So that's why you can only have one, because if I had more than one, I already have too much going on in there inside my angles. Okay? Then you guys are really good about telling me about the obtuse, where again, one angle is an obtuse angle. You can't have more than that because obtuse means you're bigger than 90. If I have two angles bigger than 90, then my triangle doesn't exist again. because I will be over 180 degrees. And then there's one more, and this is the one that generally most people are like, what do you mean, Mr. Armstrong, there's one more? There is one more that deals with the angles, okay? And it's a lot like equilateral. Most of the time what happens in the class is the students end up looking this one up. And what they find is that they find the fourth one about angles is what we call equiangular. Equiangular, where all angles are congruent. And we're going to talk about a special relationship between these two and the fact that what does it mean when all angles are congruent? Because if you have a triangle that is equiangular, then that tells you a lot about its angles already without having to do anything, just based off of the word equiangular. So again, these are the different types of triangles we have. We name it by its sides and we name it by its angles. Okay, so generally we would say like isosceles acute, or scalene right, or equilateral equiangular, okay, or isosceles obtuse. You pick one from the side, one from the angle, and you put it together, and that's the name of your triangle. It doesn't really matter which one comes first or second. I've been going from the side to the angle. I could call it right isosceles. That works just fine too. Okay. All right, so let's talk about some special properties with triangles. And these properties that I'm giving you, there are lots of special properties, but these properties that I'm giving you right here, these are going to help you throughout the assignment. So I've highlighted the properties that you need to be able to remember in order to get through your assignment, and these help make things a little bit easier, okay? So special properties. The first one is with isosceles triangles, okay? In an isosceles triangle, I want you to know that the two sides that are congruent, and this is how we label congruent sides with a little dash, okay? Congruent, congruent. The two sides that are congruent, they call those the legs, okay? The side that is not congruent is called the base. Please understand, for the base does not mean bottom, okay? Base is just, if I turn it upside down, again, these are still the legs, and that's the base, even though this is at the top. Base does not mean bottom, all right? Please understand that. Base does not mean bottom. So let me turn this back around. So the legs are the congruent sides. The base is the non-congruent side, all right? So if you have an isosceles, what they want you to know is that there are two base angles that are congruent. So the two angles that are attached to the base down here are congruent to each other. And that's always true for an isosceles triangle. If you have isosceles, then the base angles are congruent. Oh, look at the double arrow. That's a biconditional. So it's true both forwards and backwards. So if you know that base angles are congruent, then it means you also have an isosceles triangle. Okay? But the big thing I need you to know is that if you have congruent sides in an isosceles triangle, the angles that are attached to the base are always congruent. Okay? All right, scrolling on down. The next one we're going to talk about is equilateral equiangular triangles. I told you we would talk about these. So when a shape is equilateral and equiangular, we call that regular. Okay, you won't see that. They really don't mention that in the book, but I wanted to mention it to you. Because it's a name. Whenever you see the word regular, it means equilateral and equiangular. Now, this is only true with a triangle. If in a triangle you are equilateral, then you are automatically equiangular. That's only true for the triangle. And backwards too, again, it's a biconditional. If you are equiangular, then you are also equilateral. Okay? So if you're one, you automatically get the other for free. Okay? Or in other words, if you're equilateral, in the end, you can just call yourself regular, which regular means you're both of these. Again, that only works for a triangle. Let me prove my point. If you go up to quadrilaterals, which you will talk about in 10.3, the square is regular, okay? It has all sides congruent, all angles congruent. The rectangle is equiangular. All the angles are right angles, but it's not equilateral. Okay? The rhombus is equiangular, but all the angles are not the same. So as I said, just because this only works for a triangle, just because you're a quadrilateral and you have 4 congruent sides doesn't mean that you have 4 congruent angles, and vice versa. Just because you're a quadrilateral with 4 congruent angles, like the rectangle, doesn't mean that you are equilateral. Okay? Now, the other thing that we know, if we are equiangular in here, we actually know what all these angles are. Because remember, all these angles have to add up to 180. So I need an angle that I can add 3 times to be 180. And that would be 60 degrees. So if you are equiangular or equilateral, you are 60 degrees all the way around. Okay? Always. All right. So moving on from there, the next one is all about a right triangle. In a right triangle, I want you to know that we know that all angles inside the triangle have to add up to 180. You guys know that. And so you could easily just say that angle 1 plus 90 degrees plus angle 2 equals 180. But I want you to know this, that if you have a right triangle, the other 2 angles, 1 and 2, are automatically complementary. Okay? And remember, we talked about complementary. It means that these 2 angles have to add to 90 degrees, which makes sense because 90 degrees between these 2 plus 90 degrees here is 180. So this is just a faster way to deal with right triangles. Angle 1 and angle 2 must add to 90 degrees. Okay? It's another property. And last but not least, we've already just talked about this. It's called the triangle sum theorem. You know that all the angles inside add up to 180. So that's not anything new. So these are 4 special properties I want you to know because they make solving triangles, figuring out angle measures so much easier. Okay? So all the angles add up to 180. In a right triangle, angle 1 and angle 2 are complementary. In other words, the 2 acute angles that are left, and these are going to be acute. Equilateral, equiangular triangles. When you have one, you automatically get the other. So if you're equilateral, you're equiangular. If you're equiangular, you're equilateral. And if you are equiangular, all of your angles have to be 60 degrees. And then last but not least, in an isosceles triangle, base angles are congruent. And they are attached to the base. The 2 angles that are attached to the base. Okay? All right. So I've given you a triangle here. Pause the video. Find out what is the measure of angle A. Okay. So hopefully you realize that all these angles in here have to add up to 180. So 120 plus 17 degrees plus whatever the measure of angle A is has to equal 180. So all you have to do is subtract 120, subtract 17 from the 180, and you get 43 degrees. Cool, cool. All right. So some of your homework's going to be as easy as this. Go ahead, try this one. Okay. So again, you know that all 3 of these angles add up to 180. So you could take 90 degrees plus 57 degrees plus whatever our angle that's missing is equal to 180 degrees. And you can solve. Again, that's the long way. Remember, I gave you a property about this. If you have a right triangle, then these 2 angles right here are complementary. So really, all you have to do is take whatever our angle is plus 57 degrees and set it equal to 90 degrees because these 2 angles have to be complementary. So in the end, all you have to do is take 90 minus 57 and you get 33 degrees. Both of these ways work the same way. If you take 180 minus 90 minus the 57, you get the 30 degrees. Okay? So but I'm just trying to give you a way to speed things up. These two angles right here have to be complementary. That was that property that I just showed you a couple seconds ago. Okay? All right. So go ahead and try this one. Again, you can find any angle you want. You don't have to start with number 1. But I will tell you on this one, you really do need to get number 1 before you can do anything else. Okay? And pause the video, go. Okay. So hopefully you recognize that this right here is a linear pair. So yes, we are bringing back all that information from 10.1 and we're going to use it again. So that's a linear pair. Remember, linear pair are supplementary. So 180 minus 140 gives you 40 degrees. Hopefully you also noticed in here that there is a triangle right here where it has two sides congruent. So that means this is isosceles. That means that base angles are congruent. So that means this is the leg. This is the leg. So that means this guy right here is the base. And the two angles attached to it have to be congruent. So angle 1 and angle 2 are congruent. So since we know that angle 1 is 40 degrees, we know that angle 2 is 40 degrees. Okay? And then as we keep moving on from here, we have 2 and 4 right there. Again, they're a linear pair. And I didn't have to go to 4. I could have found out what 3 was right now because we know that this guy right here is 40 degrees. We know that angle 2 is 40 degrees. You could use your triangle sum theorem to find 3. We'll do that here in a second. But I saw a linear pair first, so I wanted to go ahead and deal with that, okay, for angle 4. And so these two have to be supplementary. And so 180 minus 40 gives you 140 degrees. Notice how I also put that information out here in my picture. Kind of helps me to remember everything. And then now, we can go back and we do number 3. Or, real quick, look at these two. These two angles are directly across from each other. That means they're vertical angles. And since these are a different measure than the 40, I got to do 2 arcs. So if angle 4 is 140, angle 5 is 140. So again, vertical angles, linear pairs are coming right back at you. And then now, just using the triangle sum theorem, you can figure out what measure of angle 3 is, because angle 1, angle 2, and angle 3 all have to add up to 180 degrees. Well, 40 plus 40 is 80. 180 minus 80 is 100. So there are all the angles in my picture. You got to know those properties. That's why I told you about the isosceles one, because I know there's an isosceles triangle where they want you to figure out angles in your assignment. So make sure you keep that in mind, okay? Look out for isosceles. All right. And go ahead and try this one. Keep an eye out. Now look, I've given you some things here. Notice that sign right there. What does the filled in triangle mean? Muy bien, as Dora would say. That means parallel lines, okay? So you got parallel lines. You're going to need to use that. You also might have some vertical angles you can use. You might also have some linear pairs that you can use. So keep that all in mind. And triangle sum theorem. You do not have an equilateral or isosceles triangle in here. There are no congruent marks here to confirm that. So do not automatically assume that these are all 60, even though this looks equilateral. Okay? Do not assume that this is isosceles because these two sides look like they are the same length. Do not ever assume things in geometry. That is bad math, especially in geometry, because this is not equilateral, equiangular, or isosceles. Okay? So be careful with that. but you do have parallel lines, so keep that in mind. And pause the video, go. All right. So what I start out with is I start finding easy angles. Like for instance, I know that 64 and 1 are vertical to each other. And since they are vertical, they are congruent. So that means the measure of angle 1 is actually 64 degrees. Now, the measure of angle 2, the measure of angle 3, I can't figure those out. The same thing with number 4 and 5. I can't figure out these 4 angles just yet. That's what I was saying to you, when we were finding angle measures back in 10.1 and a couple seconds ago. You don't always go in order. Sometimes we can figure out the measure of angle 1, but sometimes we can't. So what are some other angles we know? Well, we know that 96 degrees, and I'm going to use 2 marks for that, is vertical to angle 7. So I know that angle 7 is also 96 degrees. And I'm going to mark this up here. This is 64 degrees, and this is 96 degrees. Some other angles that I know that are real quick. Since these are parallel lines, I know that 64 degrees and 10 are also the same because they are corresponding. Lower left-hand corner, lower left-hand corner. So angle 10 is 64 degrees. And 10 and 9 are vertical to each other. So we also now know that angle 9 is 64 degrees. Okay? And so these are what we know right off the bat. These are what I call simple angles, using vertical angles and corresponding. Okay, or if you notice that angle 64 and angle 9 are alternate interior, could have also used that. Lots of ways to get at this, but again, remember how I said in 10.1, it's important that you know some of those vocabulary words because that gives you access to the picture. So now I start figuring out some of those other angles. This is where I would start looking for linear pairs. And we definitely have some linear pairs. 96 and 6 are a linear pair, or 96 and 8. These two are a linear pair, or 96, angle 7 and 8 are a linear pair, or angle 7 and 6 are a linear pair. So you see that you got some linear pairs right here that we can deal with that can help us out. Okay? Remember linear pairs, you just take 180 minus the other angle that's given. So 180 minus 96 lets us know that angle 6 is 84 degrees. Okay, because these are a linear pair, or an angle 6 and 7 are a linear pair. 84 degrees. Because again, you had a linear pair right there. And then also 6 and 8, they're across from each other. 1, 2, 3. 1, 2, 3. So these are vertical angles. So we know that angle 8 is 84 degrees. And now we can start attacking 2, 3, 4, and 5 because now we have lots of information that can help us out. Okay? So let's start talking about 2, 3, 4, and 5. Right now, we could find the measure of angle 4 because right here we have a triangle and we've got two angles, 64 degrees, 84 degrees. Whatever 4 is has to give me 180. So 180 minus 64 minus 84 gives us measure of angle 4 is 32 degrees. See why I said this is not equilateral or equal angular? Because these aren't even 60 degrees in here. And it's not isosceles because these two angles, I don't have any two base angles that are congruent to each other. Okay? Now what's cool, again, 4 and 2 are right across from each other. So they have to be the same because of vertical angles. 2, 3, 4, because it's an entirely new angle. 3, 4. So this is 32 degrees for the measure of angle 2. Okay? Now, let me talk to you about a couple different ways we can figure out the last angle. Okay? So, the last angle, we know that these two have to be congruent, okay, because they're vertical. 2, 3, 4, 5, because it's going to be a different angle. Well, wait a minute. Nope. We'll talk about these. So we know that these two have to be congruent. I'll do the congruent symbols here in just a second. Almost kind of gave something away that I didn't want to yet. So right here, if we start here and go all the way around, how far did we go in a circle? If I went from 64 degrees right here all the way around, you bet, that's 360 degrees. And we know that these two have to be the same. So you could take 360 minus the 64, minus the 32, minus the 64, minus the 32. And you got a number that makes up these two, which are the same. So if you cut that in half, now you know what these two are. So you could use 360 degrees to help you find out angle 3 and angle 5. Or if you look right here, 64, 32, and 5 make up 180 degrees. Okay, kind of like a large linear pair here, made up of 3 angles. So we could take 180 minus 64 minus 32, and that will give us angle 5, and then use vertical angles to get angle 3. Or we have parallel lines here. Angle 8 and angle 5 are congruent to each other because these are corresponding. Lower right-hand corner, lower right-hand corner. Or alternate interior, angle 6 and angle 5. Okay? So you actually already know what angle 5 has to be. And it's going to have 3 marks. That's why I had to erase all that. I was making 5 marks, and it's really not 5, it's 3. So we now know that angle 5 has to be 84 degrees. Corresponding, alternate interior, using 360 or the 180. Lots of ways to get that. And since 5 is 84, so is 3. So lots of ways to get through this. It's all about what you see and the vocabulary that you know. So there's all of our angles from 1 to 10. Again, it's going to be up to you to know that vocabulary. Help you to get through this. Okay? All right, good work. So let's talk about similarity. And I feel like I skipped one. Yeah, there we go. So similarity. When you guys learned about triangles in high school, you learned about, congruency between triangles. And you had side congruency, side angle side congruency. Well, we're not going to worry about congruent triangles. What the book wants us to worry about is similar triangles, because with similar triangles, we have a lot more versatility that we can do. We can do a lot more real world situations with similar triangles. It's kind of cool. Okay, so we're going to talk about similar triangles. This little squiggle right there means similar. Okay, no longer means negation. Okay, so this means similar for us. So similar triangles. It takes 2 things for triangles to be similar. This is the definition. 1, all corresponding angles have to be congruent. All corresponding angles have to be congruent. Okay? And 2, all corresponding sides are proportional. Okay? All corresponding sides are proportional. If you meet those 2 things, then your triangles are similar. So let me show you what I mean. So I got 2 triangles here. Okay? And these triangles are similar. I think I say that right. Yep, right there. Triangle ABC is similar to triangle DEF. Okay? A and D are what we call corresponding angles. They are in the same position. Lower left hand, lower left hand. So these are corresponding. B and E are in the same position. They're at the very, very top of our triangle. These are corresponding. C and F corresponding. Lower right hand, lower right hand. Since these are similar, that means that angle A has to be congruent to angle D. angle B, whatever it is, has to be congruent to angle E. Okay, notice I gave it 2 marks. Even though this thing looks equilateral, okay, it's not. You can see your sides, 6, 8, and 10. That's not equilateral. Okay, so that means these angles are going to be different degrees. And then last but not least, because we are dealing with corresponding, angle C and angle F are also congruent because they are corresponding. See, it's like matching. When you take your angles, it's like matching up the angles that go with the other angles, okay? Just with similar, you got a small figure and a large figure, okay? All right, so if I scroll down, you can see what I just talked about right there. Uh-oh, why did my angle F go over there? That's weird. That shouldn't have happened. There we go. Don't know why that happened, but it did. So angle A is congruent to angle D, and I show that in the picture. Angle B is congruent to angle E, and angle C is congruent to angle F. That's because those are corresponding angles. Okay? Now, sides proportion. When we talk about sides being proportional, you need to kind of make a choice for yourself. Go from big to small or small to big. So do we want to compare from the big triangle to the small? Or do we want to compare from the small triangle to the big? It doesn't matter which way you go, just be consistent. If you start with big to small, you got to go all the way through from big to small. Okay, if you start from small to big, then you go all the way through from small to big. And what we want to see, corresponding sides are proportional. So that means we match sides up, like what you see right here. AB corresponds with DE. Okay, so this is like the upper left side. BC matches up with EF. This is the upper right side. Okay, 8 and 4 match up. And then down below, the bottom side, AC matches up with side DF. So those are corresponding sides, and we just want to see what it means to be proportional is that they are all the same fraction. So if I put 6 over 3, which when reduced, that gives you 2. Okay? Does this fraction match the 8 over 4? Yes, it does. It reduces to 2. Does this fraction, 6 over 3, 8 over 4, match the 10 over the 5? And absolutely, that's 2. Okay? So since all these are the same fraction, they are what we call proportional. Okay? If we went from small to big, it would have looked like this. 3 over 6. I don't know why I put the equal sign in the front. That's weird. 4 over 8. 5 over 10. And that is still proportional because all these would have been a half equals a half equals a half. They're all still the same fraction. Okay? Because really what similar triangles are doing, or similarity in general, is like Ant-Man. Okay? Ant-Man is a great example of similarity. Because as a normal human, you know, his arms, his head, his legs, his feet, I mean, they're all the same. And then when he presses that button and uses those PIM particles and shrinks down, or even grows larger, his arms, his legs, and all that stuff are still proportional to when he was a human. If you compared those, all of him either blew up or shrank down the same amount. Okay? Because if that didn't happen, then he would look really weird. Okay? So Ant-Man is a great example of blowing an object up, making it bigger, or what we call an enlargement, or shrinking it down. Okay? And shrinking down, what was that? Compressing? I think we call it compressing. Enlargement, or I think it was compressing. I can't remember the other name off the top of my head. I'm sure it'll come back to me later on. So, yeah. Oh, reduction. That's what it was. Enlargement or a reduction. Okay? Other examples of similarity, generally when we're in class, you know, my screen, you know, I project everything up onto the board. So it's coming from the computer that I have. So my computer screen shows me what we should be seeing up on the board. And up on the board, it's so much bigger. Okay. That is an example of similarity because everything that's on my computer screen has been enlarged the same amount onto the board. Okay. So that's another example of similarity. All right. So what's going to happen to us in our assignment? So here's what's going to happen. Oh, sorry. Let's talk about faster ways of similarity because the definition, while it's great, we don't always get all this information. And with the definition, there are like 6 pieces of information you have to verify. You got to make sure that all angles corresponding are congruent, and then you got to make sure all sides corresponding are proportional. But there are faster ways to do this. Okay? So let's talk about these faster ways, and I believe I have 3 of them, if memory serves me correct. So, faster ways to similarity. The first way is angle-angle similarity. Okay? So, angle-angle similarity means that if I have in 2 corresponding angles, 2 sets, that are congruent to each other. So like angle A is congruent to angle D. We know that. Angle B is congruent to angle E. We know that. If that is true, I've got 2 angles that are correspondingly congruent, then your triangles are automatically similar. See, that's a lot faster. All I need to know is I got 2 angles that are congruent to each other, corresponding, of course, and I got similar triangles. Okay? We call that AA similarity. Alcoholics Anonymous. All right? Another one, you probably saw this when I was dipping down a little bit, is side-side-side similarity. Okay? All you need to check for side-side-side similarity is that all the sides are proportional. So you don't have any angles in here. We just want to make sure that if I go from big to small, all my comparisons are the same. And I just use the same numbers that we had on the other side. So 6/3 is at the same fraction as 8/4. Is at the same fraction as 10/5. Okay? Or if I went from small to big, are all these the same fraction? 3/6, same as 4/8, the same as 5/10. Okay? As long as all 3 of these fractions are the same, you have side-side-side similarity. Okay? And then not last but not least. So this one is side angle side. Yeah, that is the last but not least one. Thought I had one more. Side angle side. Okay? Side angle side, when you look at this, you want to check that the 2 corresponding sides are proportional. So again, if you go from big to small, 6/3, is that the same thing as 8/4? And it is. Or if you went from small to big, so is 3/6 the same thing as 4/8? And those both check out. But you also have the angle, and this is what we call the included angle. This is the angle between the 2 sides. Or in other words, these 2 sides form that angle. So we want to also make sure that this angle right here for us, angle B and angle E, is also congruent. So as long as these 2 sides are proportional and the corresponding angle between them is congruent, you have side angle side similarity. So these are the 3 similarity cases. Okay? Angle angle similarity, side 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 similarity, or side angle side similarity. These are the only ones they want you to know. That's it. Okay? So in your homework, what's going to happen is they're going to give you a picture of 2 triangles. And they're going to say, okay, are these similar? And then down below, it's basically going to have one of these 3 written out in words. Angle angle similarity, side 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 similarity, side angle side similarity. Okay, it's going to be written out all in words saying what's congruent and what's not and what's proportional. So you just read based off of what you have marked up on your picture. And then after that, it's going to have you find a missing side to your triangles. Okay, so let's take a look at I mean by all that. So it's like two parts. Tell me why are they similar, and then find a missing side. Okay. So here's an example. Okay. So if you look at these, why are these similar? Well, a couple things you should notice. Notice all my angles are congruent, corresponding, of course. This corresponds with that angle. This angle corresponds with that angle. This bottom right-hand angle corresponds with the bottom right-hand angle over here. So you could talk to me about angle-angle similarity. Because I only need two. I have all three. Yay! So down below in your multiple choice, you could look for something that says, oh, all angles, corresponding angles are congruent. That's angle-angle similarity. So you could look for that. Or if you notice, we can't use side, side, side. So those of you who say side, side, side similarity, we can't quite do that. Reason why? You can't use any of those cases when you have a variable. Okay, so I can't look at all three sides and know if they're proportional or not because I don't know what x is. Okay, so you can't use side, side, side. But we do have this side that matches that one, the 36 inches that matches the 12 inches, and you have the angle that is between them. So we could check and see if side, angle, side similarity works. Because it could be possible maybe they don't have the angle-angle similarity. Maybe down below they have side, angle, side. So if we check this, I'm going to go from big to small. Okay? But it doesn't matter. You can go from small to big. You just want to make sure that the fractions are the same. So if I go big to small, and I always write this out to the side, on my big triangle, I have 18. What side matches it on the small? The 6. I want to know, is that the same fraction as on my big triangle, I have 36. The side that's corresponding with it on the small is 12. So I want to know, are these the same? Well, 18 divided by 6 is 3. 36 divided by 12 is 3. So yes, these fractions are the same. So you could conclude in the end that it could be either one of these two answers. Okay? So down below on the multiple choice, either look for the angle-angle similarity or look for the side-angle-side similarity. Okay? All right, now that we know that these triangles are similar, we want to find out what x is. Okay? So let's find out what x is. Didn't mean to do all that jazz. So in order to find x, we're going to set up a proportion and use cross multiplication to solve. So again, this is where we can go from big to small or small to big. It's your choice. Let's go small to big since I did big to small to check real quick. So now, whatever I do, I'm setting up a proportion. A proportion looks like a fraction equal to a fraction. So this is like a proportion, okay? And in here, I need to get x, okay? So since I'm going from small to big, let's just go ahead and start with the x on the small. So I'm going to put that right here. Who matches up or is corresponding with x on the small that is on the big? Well, if you go over here, 15 matches it. It's corresponding. So there's my first piece. X corresponds to 15. And now I have x in my proportion. I'm definitely going to be able to solve. And then all you do is, really what you're going to do is you're going to pick one of these two fractions right here and you're going to plug it in. But again, we're going small to big. So I can either choose the 6 and the 18 matches it and call this 6 over 18. Or I could have put the 12 on top and the 36 on bottom. It doesn't matter which one you use. You're going to get the same answer. I promise you. Okay? So either 6 over 18 goes here or 12 over 36. Your choice. But the x over 15 had to be there. Okay? So again, all we do to solve proportions, cross multiply. X times 18 is 18x. And 15 times 6 is 90. Divide by 18. Divide by 18. And that gives you 5 inches. Don't forget your label. Okay? And there you go. See, not that hard, right? Nothing crazy. So up here, again, tell me why we know these are similar, and then do a little bit of proportion work to find that missing side. Go ahead, try it again on this one. And yes, these two things are really connected here. It should look like this. Yeah, they're connected here, okay? They're not separate, just so you know. Go ahead, pause the video, tell me why we know this is similar, and then solve for x. Okay. So obviously you see you can't use side, side, side on this because we don't know what this long side is. Okay, we don't know that guy. So you can't use side, side, side similarity. You can't use side, angle, side similarity either. Again, you have this unknown x here. You can't say that two objects are similar when you can't verify that both of them are the same fraction. So the only one that we have left is angle, angle similarity. And these are similar because of angle, angle similarity. How do I know that? Well, first, we have right angles. And right angles are always congruent to each other. Okay? Next, this is why I pointed out that, yes, these are connected. Because these should be vertical angles to each other. And vertical angles are always congruent. So right there is why you have angle, angle similarity. Because you have two corresponding angles that are congruent to each other. All right? And then if we're going to solve, so let's go big to small. So give me something on the big. And again, remember, we're making a proportion to solve. So on the big, let's go with x. Who matches it on the small? That's the 6. On the big, we'll go with 24. Who matches it on the small? The 12. Okay? All we do now, cross multiply and solve. Plain and simple. So x times 12 is 12x. And 6 times 24 is 144. All we do now is divide by 12. And x is equal to 12 inches. And there you go. Okay? Nothing crazy, promise you. And there's not a lot of these. I think there's like 2 or 3 of these that you have to do. Okay? All right. So, on this one, don't worry about them being similar. All I want you to do on this one is find me what the measure of x is. Okay? So don't worry about proving these are similar. Find me what the measure of x is. And I'll explain this one here in a couple minutes when we look at the next guy. Okay? And pause the video, go. Okay. So all they wanted to know is what is the measure of x? If you have a hard time looking at this, my advice to you, draw them separately. Draw them separately. So we have a big triangle. We have a little triangle. Okay? So on the big triangle, this guy is 6 inches. This length is 9 inches. This bottom length right there, we don't know. This 2 is actually from only right here to right here. So on the bottom here, we don't know that guy. So I'm going to leave it blank. That's what we know on the big. So on the small one, we know that this is 2 inches. This guy is 2 inches. And this one is x. So our directions are automatically telling us that these are similar, just so you know. All you need to do is write the proportion and solve for x. So we did big to small last time. Let's do small to big this time. So we're going to go small to big. And now, hopefully, it's a little bit easier to see what we need to work with. Okay? than when it was all together. But there's nothing wrong with doing this all together. Some people can see that. I can do that. But again, I've had lots of years of practice. Okay. But let's just do these separately. Okay. So we're going small to big. So let's grab something on the small. Let's grab the X to make sure that that's in there. Now, who matches the X on the big? That's the 9 inches. So these two are matching up. Okay. Then let's grab on the small. We can't grab this one. The reason why we do not grab this one is because there's nothing over here on the bottom. Okay. So it doesn't make sense to grab this 2 inches. So we're going to grab that 2 inches. The one that's a little bit more vertical instead of on the bottom. And that matches up with the 6 inches. That's right there. Okay. So now that we have everybody matched up, we can now solve. Oops, that was supposed to be black. So 6 times x is 6x. 9 times 2 is 18. Divide by 6, divide by 6. X equals 3 inches. And there we go. And again, these triangles are similar, I promise you. Okay? So let's talk about that when it's actually in terms of a problem. With similar triangles, there are lots of things you can do. It's what we call indirect measurement, okay? So we're going to use similar triangles to solve this problem because I've got this tree. I want to know how tall it is. And you're not going to see Mr. Armstrong shimmy up a tree just with a tape measure to figure out how tall it is. That would be dumb on my part. Most likely I would end up falling, getting hurt. You would have to have a new professor, and then you would all be crying because you wanted to take Mr. Armstrong's class because of his Flavor Flav, and now you don't get to. Okay? So you're not going to see Mr. Armstrong shimmy up a tree. Or let alone, again, usually in class, I relate it to the flagpole that we have out in front of the main entrance of our Poinciana campus. Okay. And I'd be like, I want to know how tall that flagpole is. Again, you're not going to see Mr. Armstrong shimmying up the flagpole because, again, Mr. Armstrong would probably fall, break his neck, then I'd be quadriplegic, and that would just be not good for Mr. Armstrong. Okay. And you guys would have to have another teacher because you'd all be crying and you don't get the Mr. Armstrong Flavor Flav. It's just a mess. Okay. We don't want that to happen to Mr. Armstrong. And let alone the security guards would probably also come out and tase Mr. Armstrong just because he was being stupid and trying to climb the flagpole. Okay. No one wants to see Mr. Armstrong get tased. All right. But what we would use is indirect measurement. Some things that we can actually measure from the object, like their shadows. And we can measure our own personal shadow. Okay? Because what's interesting is when you are dealing with this kind of situation, the sun hits all of us at the same angle. Okay? So if I have a tree that looks like this, and then there's me that's standing out here. Okay, the sun is coming down and hitting all of us at the same angle. That's a horrible line, but really close to what I'm trying to illustrate. Okay? And then, of course, you got your nice little grass down here. Whee! Grass, 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 grass. Do you see your two triangles? Of course you do. Because it's kind of the same picture as this guy, except instead of slanted lines, all of our lines in here are perpendicular, going right through us. Okay, so you got this big triangle that's right here, and you got this small little bitty triangle that's right there. Okay, and since the sun is hitting us at the same angle, that means this angle and this angle are the congruent to each other. And then we are right triangles because we stand perpendicular to the ground, hopefully. So there's your other congruent angle. So these two triangles are congruent because of angle-angle similarity. which is the same idea that's going on in here. Okay? These two angles that are right here are the sun hitting them at the same angle. And then down here, these two are going to be the same as well. Okay? So these triangles are congruent according to angle similarity. You didn't really need that, but I wanted to emphasize that point. I think it's important that you understand why these triangles are considered similar. Okay? And it's really because it's kind of like the same idea of the sun. The sun hits us at the same angle. All right. So now let's fill in some things that we know. So we know this person is 6 foot tall. Okay? And is standing 143 feet from the base of the tree. So from here to here, that's 143 feet. That's a horrible 3. Let's fix that. Okay? It says the tree casts a shadow of 154 feet. So let me change this. So the tree's shadow from there all the way out to there is 154 feet. The person's shadow is 11 feet in length. Okay, so I'll use a different color. This right here is 11 feet in length. What is the height of the tree? So they want to know that. Okay? So we already know that they're similar. You don't have to prove that they're similar, but they want you to find the x, just like what we did back in here. We didn't care if they were similar or not because we told you that they are similar. Just like in here, they said use similar triangles. So we already know that they're similar. Okay? All you need to do is find the proportion that we can use to solve. All right? If you have trouble seeing this, then separate them, just like what we did before. So you got a large right triangle. You got a small right triangle. So let's talk about the large. So this guy right here represents that height of the tree. So that's an X. This guy right here represents the shadow of the tree. That's what's in blue. This is 154 feet. Do not say it's 143 because that's not a full triangle. See, my sunbeam goes all the way across, okay, and ends right here. If you stopped at the 143, that's not a triangle. There's no line there, okay? So there's that. Now, on the small triangle, we know that this is the 6 feet because that's our height. And then we know that our shadow is 11 feet. Now you can see what you need to do in order to create your proportion. So this will be X. Oh, I'm going to go from big to small because I believe we did small to big last time. So I'm going to choose X, and the side that matches it on the small is the 6. And then I'm going to have 154 because we're going big to small. And the side that matches it is the 11. So all I have to do now is cross multiply to solve. So 11 times x is 11x. And 6 times 154 is 924. So we divide by 11. Divide by 11. X is equal to. And they will have you round on this one if it has to round, but it actually comes out nice and neat. The tree's height is 84 feet. And again, you know, safety reasons, you would not see Mr. Armstrong climbing an 84-foot tree. You know, don't get me wrong, I can climb trees. But I'm getting older. I don't want to climb a tree because if I fall, it's probably not going to be good for me. All right. So there's similarity. Now we're almost done. Last but not least, in this section, we're going to talk about the Pythagorean theorem. You all know the Pythagorean theorem. That's not new to us. Most of the time when I say, give me the Pythagorean theorem, you're all like, a squared plus b squared equals c squared. And I'm like, yes, a squared plus b squared equals c squared. Okay. Now, with the Pythagorean theorem, just some things I wanted to kind of tell you about since, our geometry has such a rich history. The Pythagorean theorem is quite interesting. It was discovered by a gentleman named Pythagoras, and there's actually a whole cult that was built around the Pythagorean theorem. Interesting. And some of the things that happened in this cult is that there are many people that believe Pythagoras stole the Pythagorean theorem from someone else, and they killed him over that. His cult did. So it was kind of interesting. He's credited with it, but there are people out there, I'm sure, that exist that believe maybe not. Maybe he is not the one that really discovered this. Okay, it's kind of interesting. It's fascinating. Go look it up. It's got definitely a tale of mystery behind it. So, as I was saying, we're going to talk about the Pythagorean theorem. You already know what the formula is. And a squared plus b squared equals c squared. Here is your right triangle. Just some things that I always like to tell you. The legs always form the right angle. There's the right angle. These are always the legs. Okay? A and B are always the legs. I can't stress that enough. C is what we call the hypotenuse. Okay? Remember, the hypotenuse is always the longest side. Okay? It is directly across from the right angle. All right? So, the legs, the A and the B, form the right angle, always. The largest side is C. It never fails, but I will have someone in here take the C value, the hypotenuse, and actually put it in for a leg. It never fails. So just please, please, please be careful with that. Okay? The legs form the right angle. C is the hypotenuse, which is the largest side. It is across from the right angle. All right? So what they're going to give you in your assignment, here's a right triangle. Solve for x. Go ahead, pause the video, and do that. Go. All right. So hopefully you noticed that I gave you the legs. Here's the right angle. So one of these is A, one of these is B. Which is which? It doesn't matter. I'm going to call you A, I'm going to call you B. Does not matter which one is which. And that guy obviously has to be C because it is across from my right angle. Okay? Plugging into A squared plus B squared equal to C squared. Here's how this is going to happen. This happens in 3 steps to get to the answer. And it always works like this. Step number 1, we're going to do some squaring. Okay? So once we plug in, 8 squared plus 6 squared equal to C squared. Or you can put X there. Let's go ahead and put X since that's the variable they gave us. But you can keep it as C. It doesn't really matter. So the first thing we got to do is square. 8 squared is 64. 6 squared is 36 equal to X squared. So step 2, you're either going to do some adding or subtracting. In our case, this time it's adding. But if I knew a leg and a hypotenuse, you would be subtracting. Okay? So it's either adding or subtracting. It's not both. So we're going to add because these are like terms. In other words, whenever you have both legs, you will add. If you have a leg and a hypotenuse, you will subtract. Okay? It always works out that way. So 64 and 36 give us 100 equal to X squared. Last step, you will square root. Because how do I get rid of something squared? We square root it. Square root square root. Now, normally when you take a square root of both sides, I will harp on you and say that your answer should have a plus or minus in front of it. And the square root of 100 is 10. This is technically the correct answer. But because we are dealing with a triangle and these are side lengths, lengths have to be positive. You cannot have a negative length. I do not know what a negative 10 inches, I think it's inches, would look like. So in here, I'm going to forego talking about the plus and minus, and it will always be a positive answer. So the square root of 100 is 10, and it is 10 inches. There you go. 3 steps. After you plug in, you're going to square, then you will add or subtract, and then you will square root both sides. Don't forget the label. Okay? Easy peasy, Pythagorean theorem. All right, your turn. Go. Okie dokie artichokes. So we've got a squared plus b squared equal to c squared. So what do we have up here? Well, I'm going to call this a. You could call it b if you want. It doesn't matter. It's a leg. And then we'll call this guy the b. Okay? So we got a, we got b, and c. So what I have up here is I have a leg and a hypotenuse. That means I now know in step 2 I should be subtracting. Okay? So let's plug in real quick and let's do step 1. So we got 14 squared plus x squared equal to 25 squared. Okay. So 14 squared is 196 plus x squared equal to 25 squared, I believe is 625. Double checking. Yep. So you can see why we have to subtract, because I got to get x by itself. So subtract 196 from both sides. So 625 minus 196 gives you 429. And then last step, square root. So x is equal to, go to your calculator, 429, hit second x squared, because that's where your square root is. So you hit second x squared, and you put in the 429, and your calculator kicks out a long decimal of 20.71231518, and you'll read that fine print under your box of the answer, okay? And most likely it'll either say round to the nearest whole number, 10th, or 100th, okay? So I'm going to say let's round to the nearest 10th. So we're going to have x equal to 20.7, and what do we got here? Centimeters. There we go, because the 1 says, hey, 7, stay the way you are. If you're rounding to the nearest whole number, you would have had 21 centimeters, because the 7 says, hey, 0, go up. If you rounded to the nearest 100th, you would have had 20.71 centimeters. Okay? So there's all the other different roundings that you could have done. Make sure you read the fine print. And I believe that is it. Nope, just kidding. One last problem. Yeah, this is it. So they'll give you a word problem for Pythagorean theorem. My advice to you, draw a picture, okay? Draw a picture and to help you out. Geometry, it's all about having pictures to help you out, guys. Pictures are so helpful in geometry. So go ahead, pause the video, give this one a shot, and then that wraps up 10.2. And go. Okay. So it says we have a 23-foot ladder placed against a vertical wall of a building. All right, cool. So let me here. I got a building here. I got this ladder. My drawings are always the best. Okay. And it says this ladder is 23 feet. Okay. We got a building here with the bottom of the ladder on level ground 12 feet away from the base. Okay. So So in here we got some grass because we're on the ground. And this length right here is 12 feet. They want to know, how high up is the ladder? Hopefully you see your right triangle. If you don't, I'll highlight it for you. There is the right triangle because buildings are perpendicular to the ground. Okay? So now all you have to do is run that a squared. That's not the color I wanted. A squared plus b squared equal to c squared. So if you look up here, the 23, that's your c. So that means the 12 and the x, one of these is a, one of these is b. Does it matter who's who? No. So let's call x a, and we'll let the number be b this time. So we got x squared plus 12 squared equal to 23 squared. Okay? So 12 squared is 144. That should be a plus, not a minus. 23 squared is 529. So because you have a leg and a hypotenuse, you're going to have to subtract, and you can see that. I don't know why I said 144 squared. That shouldn't be there. Sorry. So we're going to take 529 minus 144. And so we will have x squared equal to 385. Last thing, square root, square root. So when you go into your calculator, you hit that second x squared, put in the 385, hit enter, and the calculator says it's 19.62141687. So if we round, again, it might say whole number, 10th, or 100th. Here are all the different possible answers. If you round to the nearest whole number, you have 20 feet. If you round to the nearest 10th, which I think is what they're going to have you do, it's 19.6 feet. If you round to the nearest 100th, it's 19.62 feet. So there are your answers. Okay? And that wraps up everything you need to know about triangles. Again, like I said, it's very surface level. Okay? So that concludes 10.2. See you next time.